Parallel universes. How science is pushing the boundaries of reality. Carl Sagan famously said, "The universe and cosmos is all that is, or ever was, or ever will be." But what if the universe we know is just a small part of something far greater? When we look at the night sky, we see only a fraction of the stars that exist. We now know our universe is home to billions of stars and galaxies, but even that might not be the whole picture. Today, we're going to explore the idea that what we see is only a glimpse, and that beyond our observable universe could lie multiverses, alternate dimensions, and realities unlike anything we've imagined. The cosmic microwave background radiation is leftover energy from when the universe was young and hot. It has traveled for nearly 14 billion years, and what we see now is called the observable universe. However, scientists think the universe continues far beyond what we can see, possibly infinitely so. The nature of the universe and Hubble volume. We're unsure if anything existed before this universe, or if our Big Bang was just a small event in a larger, older universe. It's also unclear if there are any other places with different rules, like extra dimensions or different physical laws. We often use terms like parallel universes, multiverse, or alternate realities to discuss these ideas. Currently, there is no evidence for anything beyond our observable universe, except for the notion that it continues to expand. We don't expect to be at the center of the universe, and the edge is likely just a uniform area of energy left over from the hot, dense state of the Big Bang. This means the universe is probably much larger than what we can observe. If Earth is randomly located in the universe, it should be larger than the part we can see. For example, if you're in a dark warehouse with a lantern and there are no walls in your light, the warehouse is likely much bigger than what you can see. Therefore, the universe likely extends beyond our view. But whether it's just a little bigger or infinitely large remains unproven. Mathematical theories and Hubble volume. We have some mathematical ideas about the existence of multiverses or alternate dimensions, but we currently cannot test these theories. Some sections of the observable universe may have already moved beyond the point where we could send signals to or receive signals from. This leads us to the term Hubble volume, which describes the space we can communicate with. Even in the distant future, as stars fade away, we may still not know if anything lies beyond our universe. Some theories suggest the existence of other realms, but we can't assume they exist without evidence. Max Tegmark, a cosmologist, has proposed 4 levels of the multiverse, with the first being the extension of our universe beyond what we can observe. In an infinite universe, things would repeat, meaning we'd find identical places that we couldn't tell apart. The average distance to find a repeat would be around 10 to the 10 to the 15th power meters away. Level 2 talks about universes that have different physical constants. For example, gravity or the Hubble constant, which is related to how the universe expands, might be different. This idea comes from something called eternal inflation theory, which is a variation of cosmic inflation theory. Alan Guth created this theory in 1979 to explain some big problems with how matter is spread out in the universe according to the Big Bang model. It also helps explain why the universe can appear flat and evenly distributed. Many people confuse cosmic inflation theory with the usual cosmic expansion we discuss, where galaxies are moving away from each other. But inflation refers to a very short moment right after the Big Bang. During this brief instant, the universe is said to have expanded by a huge amount, by a factor of 100 trillion trillion. This only lasted about a billionth of a trillionth of a trillionth of a second. After inflation, the universe was probably only about a meter wide or less. But even before inflation, the universe was very tiny, much smaller than an atomic nucleus. In that quick time, the universe grew immensely, even more than it has since. Eternal inflation and level 2 theories. We only know about the observable universe, which is just a small part of the whole universe. The rest could be much larger or even infinite. Before inflation, the universe was incredibly small, and that inflation was just a rapid burst of expansion. We don't have direct evidence of this inflation. We can't see further back than the last scattering event, which happened when the universe was about 300,000 years old. Inflation is believed to have occurred in the first micro-picosecond after the Big Bang. So why do we believe inflation happened? The universe is not evenly spread out. It has a large-scale structure. This unevenness suggests that a fast expansion period and tiny variations caused by quantum fluctuations must have occurred. Essentially, this theory explains why the universe isn't uniformly distributed on a large scale. We think a quick burst of inflation helped the very tiny random distributions of matter and energy grow into larger gaps instead of being evenly spread out. Now, there's a different idea called eternal inflation. One issue with regular inflation is figuring out why it should stop after that brief moment. This is known as the graceful exit problem. Eternal inflation suggests that inflation never really stopped or that it didn't stop everywhere. In some places it stops, forming distinct bubbles like our universe. This can create many mini-universes. There are various versions of this idea, but level 2 includes this and other possibilities, like the idea that each black hole might create a new universe. These new universes could have different masses and physical constants, meaning they might be less massive than ours or have slightly different forces. Once again, there's no direct evidence for these theories, but they make sense as logical consequences of other theories. Levels 3 and 4, Many Worlds and Ultimate Ensemble. Level 3 comes from the many worlds interpretation of quantum mechanics. In quantum mechanics, there are different interpretations of what happens when we measure something, like Schrödinger's cat. For example, the Copenhagen interpretation suggests the cat can be both alive and dead at the same time, until we check. In contrast, the many worlds interpretation says that every possible outcome has actually happened in parallel universes, unlike the Copenhagen view, which states that all possibilities exist, but only one occurs when we observe it. Many worlds can lead to strange implications that are often simplified in science fiction, which usually presents it as a scenario where a historical event happens differently. We explored this in our Infinite Improbability Issues episode, which many remember as the Quantum Cheeseburger episode. This idea overlaps with level 1 because both suggest an infinite universe where every possible configuration exists. In both level 1 and level 3, all configurations of the observable universe must exist. However, the levels don't depend on each other. Additionally, the many worlds interpretation isn't just about different futures branching from a single event or decision, it also allows for multiple pasts that could lead to the same result. It doesn't necessarily mean new universes pop up with every event. Instead, you can think of it as a vast number of multiverses where every arrangement of matter and energy exists, and your timeline is just the path to take you through them. Level 4 in Tegmark's classification system is the Ultimate Ensemble. This level includes every possible universe we can mathematically imagine and covers levels 1, 2, and 3. It doesn't focus on specific details, but is essentially a catch-all for everything we can think of mathematically, including ideas like a two-dimensional universe, like George Gamau's Flatland, a universe with a fourth physical dimension, or ones with multiple dimensions unrelated to time and space, not just the small extra dimensions suggested in string theory. String theorist Brian Greene describes 9 types of multiverses. The first is the quilted multiverse, similar to Tegmark's level 1. In an infinitely large universe, with travel limited by the speed of light, there are many smaller observable universes, or Hubble volumes, where every possible scenario has occurred. Next is Type 2, the inflationary multiverse, which resembles Tegmark's level 2 and the eternal inflation theory. Then there's Type 3, the brane multiverse. In this context, brane refers to membranes in string theory, not the brain you might be using to process this information. Branes represent universes like ours that float in a higher dimension called the bulk. These branes can collide or interact, sometimes causing big bangs. They are thought to attract each other gravitationally, which could explain why gravity is so much weaker than the other fundamental forces, like electromagnetism and nuclear forces. The idea is that gravity isn't confined to one universe but is spread across all branes, making it appear diluted. Greene also presents Type 4, the cyclic multiverse. In this model, branes collide and create new universes. After a while, they bounce back together, collide again, and this cycle repeats. This is distinct from other cyclic models, like the Big Crunch, where the universe expands, contracts to a point, and then big bangs again. Cyclic multiverses emphasize this ongoing process of brains interacting over trillions of years. You often hear about M theory when discussing brains instead of just string theory. They are related, but to clarify, the M and M theory usually stands for membrane, because it deals with brains. Edward Witten, who introduced the idea, also said that M could mean mystery or magic. Green's Type 5 is called the landscape multiverse, which is similar to Tegmark's Level 2. It suggests that in these extra universes that are expanding, quantum fluctuations can cause them to settle into low-energy states. This creates areas of space with different laws than the surrounding space. While this is a simplified explanation, it illustrates that the big universe is always growing, and some regions form unique universes with their own rules, while others disappear, similar to the idea of false vacuum catastrophes. Type 6 is the quantum multiverse, which relates to the many worlds idea. Type 7 is the holographic multiverse, based on the holographic principle. This principle suggests that the surface of space, like a black hole's surface, holds information about what's inside. Although it mainly involves thermodynamics and entropy, it also relates to our understanding of three-dimensional reality. Many people mix this up with simulated universes, which is Type 8. The simulated multiverse is the idea that every possible universe is created by a higher-level computer or similar system, possibly controlled by a higher power. Remember Tegmark's Level 4, which includes any universe we can describe mathematically? Simulating such a universe could be one way to create it. If we can model it mathematically, we might be able to run a simulation on a powerful enough computer. Type 9 is known as the ultimate multiverse, which is similar to Tegmark's ultimate ensemble. It includes every universe that can be described mathematically. I like to add an extra type for universes that we can't even describe or imagine mathematically. It's just my way of wanting to include the unimaginable along with what we can understand but can't observe. This is part of the challenge with multiverses. If we can't see them, measure them, visit them, or interact with them, I feel like they might as well not exist. According to Occam's razor, we should assume they don't exist. However, these ideas come from possibilities in different physical theories we've developed. They haven't been proven, but they shouldn't just be dismissed as random guesses either. That said, I don't like the common idea that these concepts should be treated as solid science, or that if one theory is correct, then all of them must be. It's more likely that some could be true while others might be entirely wrong. Things would change if we found a way to detect these multiverses. For example, if we could achieve faster-than-light travel, it might show us whether the universe is bigger than what we can currently see. However, proving that the universe is infinite is impossible because it would take an infinite amount of time to check. We could only find out if the Level 1 or quilted multiverse, an infinite or nearly infinite universe, is truly close to being infinite. Talk about other big ideas like the simulated universe or the multiverse, it's important to think about what proof we might have. If there are creators behind our universe, like a simulator or a higher power, you can call this entity whatever you like, maybe they left us clues or evidence about the nature of our existence. This could help us understand if we really live in a simulation, or if there are other universes out there. Another interesting point to consider is that many of these hypothetical multiverses might not be very lively. There's a chance that most of them could be dead or lifeless. For example, even if there are countless universes with different physical laws, some might not have the right conditions for life to evolve. Some theories suggest that these lifeless universes could collapse due to a phenomenon known as a false vacuum catastrophe. This means that finding a universe where life could develop might be extremely rare. It could be like winning the lottery, not just once, but winning it every week for several months with only one ticket each week. Now, imagine if we could travel to these other universes or even create new ones. The idea of moving to a different universe could be very appealing, whether it's a one-way trip or we could come back. The chance to explore new realities would be a huge temptation for many people. We still have a lot of questions about parallel universes and alternate realities. We don't know which of these ideas, if any, are true. If we can't interact with these other universes, it might not matter to us right now. However, if we find a way to connect with them, it could change everything we know. The universe, or the entirety of reality, could be much bigger and more complex than we've realized. There could be infinite places, an endless number of people and events, and even things that we cannot even imagine yet. This thought is both exciting and mind-boggling.